So, uh, so attendance, your attendance is basically based on this software MS Teams. Okay, just to give you an idea. So मैं actually name call करके attendance नहीं लूँगा because that for me will take more time and anyways it's not that much important right now. However, जो तुम लोग की अटेंडेंस मार्क होती है दैट इज बेस्ड ऑन व्हेन यू लॉग इन and when you log out in this portal MS Teams. So basically it generates a report ki when a person logs in or when a person logs out. So I understand connectivity issues honge and that's why we are recording these lectures and sharing with all of you. So those who are not able to directly access it for full time or not able to access it at all, sometimes they can have those recorded lectures later on. However, ऐसा नहीं होना चाहिए कि someone is there who is totally relying on recorded lectures only. So everyone, please try to at least log in sometime, because why I'm saying this, all the attendance will be logged based on how much time you are here. डोंट थिंक इट इज़ वेरी स्ट्रिक्ट. इतना वो नहीं है कि अगर किसी ने आधा घंटा पहले या कुछ डिस्कनेक्ट हो गया तो तुम लोगों का एब्सेंट मार्क हो जाएगा. ऐसा कुछ ऐसा नहीं है. दिस टाइम थिंग्स आर वेरी कंसिडरेट इन दैट सेंस, बट वी नीड द नेम्स हु आर अटेंडिंग. ओके, इट शुड नॉट बी कि कोई एक दो लोग हैं जो अटेंड ही नहीं कर रहे हैं क्लासेस. सो आई एम सीइंग एन अटेंडेंस ऑफ 35, सो डू लेट अदर्स नो. जो कि अगर ऐसा कोई है जो रेगुलरली अटेंड नहीं कर रहा है, सो लेट देम टॉक टू अस. क्या रीज़न है? बिकॉज इफ समथिंग लाइक दैट इज देयर कि किसी ने सभी क्लासेस करी ही नहीं है और किसी में भी अटेंडेंस नहीं है उसकी, तो देन देयर विल बी एन इशू. आई अंडरस्टैंड सब लोग के यहाँ कुछ ना कुछ इश्यूज रहेंगे कनेक्टिविटी के, but we need to know if anyone is not at all able to connect. Okay, otherwise फिर उसमें थोड़ा सा इश्यू आएगा. So do take care of that. हाँ, and because we were not recording that time, so lab journals have to be maintained, and you can create soft copies for now for all the lab journals. Maintain a format. The format should start with the experiment number, the aim of the experiment, date, and then continue with what we have done. Since a hard copy will be required later on, so जो भी soft copy we are making, we'll be using those as printouts later on and make a hard copy journal submission. Okay, so that is it for now. Yeah. So let's start for today's main work. So today what we'll be doing is we'll be finishing that that thing we were doing for probability distribution MATLAB exercise. I think we have already reached the stage where we have plotted these PDFs for individual C5 and unit weight, right? We will see if we can make force functions, the probability distribution function for forces, and can we compare them in a same graph to basically do something like a margin of error analysis sort of that. So that we'll see. Then we'll come to the limit equilibrium part. We'll discuss any issues that we faced in our tutorials, and we'll also see one project that was done on the basis of that, and how it was approached, what raw data there was there, and how a limit equilibrium based analysis was done to propose a stabilization measure. Okay, we'll see that case study. Then today what I am thinking, if time is there, and we'll start the finite element method. A very important method will up ahead of limit equilibrium, where many of the limitations that are present in limit equilibrium method can be actually overcome by this. And it is used in diverse fields, not just for slope stability. So we'll be discussing that. And if time permits, again, we'll be seeing how finite element method is used in our case of scenarios where uh, like slope stability or tunnel stability, or we can do some other exercises based on these finite element method. Okay, so we'll start introducing that today, and maybe in further 1 or 2 weeks we will be covering this finite element method, because yeah, we have I think on now Monday and Tuesday. So yeah, 1 2 weeks we'll dedicate to finite element method, and then we'll move ahead. Okay, so let's start today. Mm, yeah, so okay. So last time we reached, I think at this stage. Mm, yeah. So just to recap, we were making probability distribution functions. We were generating those, and what we did till now, we basically saw some randomly generated data, and on randomly generated data, we converted into the frequency distribution for cohesion, friction, and unit weight. And based on this, we did a curve fitting analysis that we learned how a curve fitting works in the MATLAB. We saw what are the parameters, goodness of fit, and so on, right? And on the basis of that, we fitted an equation that is representative of a normal distribution, a Gaussian type equation, right? That has three constants. Basically, two of them representing mean and standard deviation, and one is 1/2 pi of that standard deviation, the fractional part. So based on those, we basically calculated all these three by curve fitting method for uh, all the three distribution functions, and found that what are the coefficients for this equation, right? And we actually tried to plot it. We saw how these can be a function handle can be defined in MATLAB. So function handle basically gives a relationship between x and this y value. So y is a function of x that is represented by the equation that precedes it. So that's where we had reached. We were also seeing how plotting can be done, right? So plotting is easy. Now with just the function of f plot was used, and we gave a range from which to which range we want to plot, and a hold function that helps us in plotting multiple equations or multiple plots on the same figure. So we were plotting all these three Gaussians. So let's see where we reached last time. Okay. So this is where we could reach last time. I think last time some numbers got messed up. So this curve was fitting on the edge, but I corrected it last night, and this is something we get. So if you see carefully, what it is representing is basically this one, the blue one. If you can see carefully, it is a cohesion, and it is based on this equation that we developed, right? GC. The orange one is phi, and the yellow one is unit weight. So you can see how even though they have different units, right? Unit of cohesion is in kilonewton per meter square. Phi is in degrees, and unit weight is again in kilonewton. But what we are doing is we are basically plotting to see where it stands in terms of just distribution. And In terms of that, we have on the y-axis a probability matrix. So the probability of finding that, and on the x-axis we have some values that are defining each unit for each of these curves. So physically this doesn't make that much sense plotting all these two together, but statistically what we know is how the distribution changes for each of them, and you can see how the lower and the flatter curve is a bit broader, while the taller and the taller curves are thinner. And that's the way a normal distribution has, we have seen as we have studied it works, because the total area below this curve will always be 1, right? Because the total cumulative probability can only be 1 for any event to happen, not more than that. So these are some distributions that are there. Now, what else we can do? We want to basically find out the force and factor of safety, right? So let's do that. We have done this. Let's define more constants. Suppose area, we have to define area. So area can be say 50. Let's put in meters squares, right? And what else we need? CA, and we need the xi values or the xi p, the angle of the slope, right? For considering a typical angular problem, right? So angle of the slope, let's take 45 degrees. So slope angle, okay, slang equals to 45 degrees. Okay, and just to make us remember, we are making some comments on that. And do remember that when we do some cosine functions or sine functions, for example, let's say we want to find out what is tan 45. Just the normal functions actually take 45 as a in radians. So this has to be basically converted. 45 degrees have to be converted uh, into radians. So we can simply do it by by 180, right? It does that. So it will give us 1. So that we have to take care. So either do it during the equation formation, or we can do it in here. So slope angle in radians. So SAR equals to for slang into pi by 180. I think this should work. No, I have done some. Okay. Okay. Right. Let's put some braces. Semicolons will not produce extra answers, so that's okay. Converting to radians. Correct. Now, these definitions are already done. Let's keep them as it is. But we have to define it again. I will give you the reason. So, intuitive way to do something like this would have been just directly using our formula, that is Ca plus sigma tan phi, and sigma can be the W cos theta component or the unit weight cos theta component, right? Cos psi component. So let's do that. Let's find the forces now. So forces, uh, these are plots. So let's remain them as plots. Okay, and these are the inputs or variables. Just to segment them properly. Okay. Forces. So in forces, we will be doing force of FD, driving forces, and some force of resisting forces, right? So driving forces is weight cos theta. Weight is in terms of unit weight, right? Because this is in kilonewton. Oh, sorry, huh? This is in kilonewton, right? 24.5 kilonewton, and we also have to find the volume of that. So let's assume some volume from our calculations. Let me see. We have old our assignments are there, right? So let's use those values uh, just to see if we can work things out. Uh, where is it? Mm. So we used we had the first assignment of RST, right? So let's use those to just calculate one problem here. We already have unit weight and other values. So what we need now is just the geometry. Oh, what happened? We need now just geometry, and so let's take some units here. If this one has something, if the rock density is that's okay. This is given. This is given. This is given. So let's use this answer, the solution for this, and try to simulate. So we have this demo. Hold on. So for this question, we have area of 50 meters square that is there, and what we have is a weight of
Uh-huh.
how much weight do we have here? Which question is this? 5210 2100, right? So yeah, just a sec. Hmm. So a volume of 10147 was found for that question. So we'll take a volume of 10147, just in meters square or meter cube. Is that correct? I think so, yeah. I'm just actually getting from our assignments, I'm just trying to get a volume value. If someone has that volume, yeah, we can use T and function. That's true. If someone has that value, do tell me. I'm just calculating it. I don't know where I kept it. In our first assignment, we had some weight calculations done. So I'm just trying to find out that because that will be easy. Okay. Okay. It's not 101%, it's 1035. Right. Let's do that. Hmm. Yeah. So volume is this. For calculation of forces, we need certain more functions uh, like for driving forces, we have W sine theta, right, on the lower side. So what we'll do is we'll calculate the weight. So weight will be, let's make a function in this way, the rate x, and weight will be volume into the unit, right? So it can be the unit function, the whole this, right? Let's paste it here and also multiplied by volume. So this will be W, and we can actually enclose it in one bracket and put a sign. I think this works, right? So FD can be this. We have FR, that is resisting force. So that will be a combination of things. Let's try to do that as well. At the rate X, we have CA. So we have the equation for C, cohesion, right? So let's paste it here and we do area. So area variable is area, right? Right. Area into, so this one is CA. So keep a track of the parentheses because sometimes it gets confusing. CA plus W cos theta now. So what we can do is can actually enclose this, just because this is W sine theta, we can just copy it here and make it a cos, right? That's it. And into tan phi, right? So we'll use tan. Or let's do what Amritesh says. Let's do the tan D function, right? And directly use the values of P, that is phi, in this equation. Should work. Let's again recheck the number of parentheses we have, otherwise there will be an error. W cos theta is done and into tan phi, right? All the done. So what we can do now is let's plot this and see what happens. We need two more things. We need a difference function. So force difference equals to Fd minus Fr. That's simple. Oh, sorry, Fr minus Fd, the resisting force minus the driving force, right? And we also want to calculate the factor of safety function. So we'll do that later on. Let's first see where we have reached till now. So let's plot Fd. and FR. Let's keep this in. I don't know what the ranges will be, so let's just plot it and see if we are meeting the ranges. FT minus FR, अभी इसको हटाओ. And run. So कहाँ गया plot? So these are the plots. The good thing is both are well separated. So for our case, the difference will be too much. Yeah. So the orange one is our FD. Oh, FR, the resisting forces, and the blue one is our FT, the driving forces. So what essentially what we are measuring here is the forces in kilonewton, and the distribution is shown in terms of units on the y-axis. So how much that is distributed. So on y-axis we basically see how the force is distributed, like how much variation it will be there in these 100 values, right? And in terms of the x-axis, we can actually see how much separation is there between the force and FD and the FS. So basically what we are actually judging from here is this slope is quite stable in that sense, and there is a good enough difference between the lower side and lower side of the driving forces. Oh, sorry, the upper side of the driving forces and the lower side of the resisting forces. So if this would have overlapped somewhere here, we would have got some probability of failure. So for now, it will be almost 0% or close to 0%. Why close to 0%? I'm saying because there will be no zero values here, considering the equation is actually normal distribution. So there will be some overlap, quite very less somewhere, but insignificant. So this kind of analysis actually is what is done in the uh, marginal value that we discussed, right? So in that case, these kind of differences are seen. You can plot a difference equation and so on. So further to that, what we can do is we can make an FOS function, just divide these values one over the other, right? We can even plot a f difference function. I think something is wrong in this. Yeah, I think we can't do this. Let me check out. We can do this, I feel. Okay, I have to define this as well. Oh, my mistake. So f difference is also an x. So I have to tell the system that it is also a function of x. So it is a operating function operator, and then it will actually can do that. So if I plot a difference, I think it will be 0, but let's try. Let's try to do the plotting of f difference now. Uh, let's see what comes. Now this is old. Where is the new one? Yeah, so it is giving a zero line actually, because according to this there is no overlap. If there would have been, there would have been a normal distributed curve. So that's it. So on similar sort of analysis can be done for all the Stoke cases. We could have made actually the data we could have made with respect to what we did in one of the examples. I should have remembered that, so that would have been more useful. But anyways, the whole purpose is to see how things are done. So what we saw here is basically how functions can be plotted in MATLAB, right? How the functions are defined, the operator functions are defined. These are called function handles, right? And how these equations can be defined, how the curve fitting is done, and how we can basically write a code to basically plot them and see them with respect to each other. So that's the whole exercise. I'll stop here. We can also try and find the factor of safety and plot that. So do that. Try doing that and see what you get. It's just simple factor of safety. You have to define it as at the rate x, and you can just use these equations to define the factor of safety. Try plotting that and seeing how it is coming. I'm pretty sure it is much more than 1, so that is good. So do try that. Do see how what is the distribution of factor of safety. I won't be doing it now because I have to move on. This has taken a lot of time. I was not expecting that. Try doing a factor of safety calculation similar to what we have done here. Use these values, or by your own curve fitting you can try. Try to do for that assignment we had. Try to do for some example using that assignment and see what you are getting, what driving forces and resisting forces you are getting, and what will be the factor of safety and how it is distributed. So try doing that. I will let's see how things turn up. Basically what we want is whatever our those assignments were there, try taking any one of these examples, right? We had these assignment, so try taking any one of these example and try finding the FD, FR, F different, and FOS, the four things that can be plotted, and try plotting those individually and with respect to each other and see how things are. And this will actually give us a probabilistic approach of doing this. Okay, so do that. Try doing that and let's see what happens. Okay, I'll be stopping here. And any questions till now in this with respect to probabilistic distribution, probabilistic study, and what we did in the MATLAB exercise, what we understood? Any questions in that till now? No. Okay. So this can be taken as an assignment. I think just take one question, a small assignment this time. For next time, just take, or rather than doing an assignment, keep it as I think a lab work. That will be much more useful. So keep it as a lab experiment. Use any of these assignment problems, 1 to 5, right? 1 to 4, sorry. Fifth one was the derivation. So use any one of those 1 to 4 assignment problems, take it up, try doing all this, make a random variable generation for C, phi, and unit weight, right? Do calculations for that and find a probabilistic approach for this. Just one question, don't do it for all. Choose any one, whichever you like, do it and keep it as your lab journal work, okay? Find the distribution functions of force, find the distribution functions of resistive force and driving force, find the distribution function of FOS. So FOS I'm not doing, try it out yourself. Do share your results and see how things are coming. Okay, clear this till here everything is clear. समझ में आ रहा है? So let's move ahead. ये इसको close करते हैं. We'll close the probabilistic analysis now. MATLAB will keep on coming back and forth whenever use will be there. So for now, we'll uh, keep away with the MATLAB. Okay. Yes. So let's come to now limit equilibrium method. Uh, any issues with the tutorials? Did you guys have time to go to the tutorials? Amritesh said he did. There were two questions with him. Anyone else? Any questions regarding tutorials? Any work regarding any work you did in the slide software that gave some results that were not clear, or something that you found interesting? Do share. What happened in... So tutorial 10 is water table statistics. Okay. Mhm. So what was the issue in this, Amritesh? What were the issues that were coming in this tutorial? Amritesh?
Hello.
Yeah, Amritesh.
Hello. Yes, sir. So when I was trying the tutorial,
Mhm.
miss 1 minute.
Mhm.
Hello.
Yeah.
So after doing the modeling,
Mhm.
okay. So when I saved the file and compute it, uh, it showed that there were no failure surfaces found.
There were no failure surface found. Okay, okay. Let me check it out. In this, at least, I'm seeing some failure surfaces are there. Yeah, failure surfaces are there. Amritesh, what you can check out, I'll give you two things. First thing is properly defined grids. Okay, do check this out if that is properly defined. Okay. Second thing is do check these slope limits if they are properly placed. If these are also disturbed, maybe sometimes very close away, something happens and it is very close. Do check this out if these are the problems, because from what I am doing here, it's basically nothing different from what we did in our previous tutorials, just that it's doing some sensitivity work and some groundwater under the level of water surface. Properties are defined as usual, and it has given a grid search, and a grid is defined, right? So do check the grids, do check these limits, and then see, because right now when I interpreted it, uh, let's do that again if that's a problem. So it's giving some surface at least. So maybe some of those things can be checked out. No failure surface found. What other reasons can be there? One of the reasons.
So when
Yeah.
I go for the sensitivity plot, uh,
Oh, when you go for the sensitivity plot, hold on. Okay. Uh, you're not getting this?
no, so afterwards it says to open the second tutorial file. After this plotting, the next step is to open the second tutorial.
Let me read. I have maybe skipped something. Just let me read what it says in the interpret portion, right?
After interpreting, open the tutorial file.
Yeah. For this demonstration, we will read in a different file, right? Tutorial 2, it is starting.
Yes, sir.
And then notice the file we have read in already includes a deterministic water table.
So
After that, you did a probabilistic analysis in that, right?
probabilistic.
You did a probabilistic and you did for maximum water, then you take a water table statistic. And in that statistic, you might not have found any that
Yes, sir.
say failure surface. Okay, let's check that out then. So for all of you, what we are doing right now is uh, this is an example uh, where a water table has been defined in there, and its ranges are given, and what we are seeing is how factor of safety changes with respect to the distance and other factors. Let me just close this first and see what they want to do now. Okay, uh, let's bring this tutorial here. Right. So just Amritesh, bear with me because I will explain everything quickly, and then we'll move ahead. Okay. So just for all of you, this is basically how the statistical analysis is done in a water table scenario. So they have basically defined maximum and minimum locations of water table, right? If this is an average one, where it will be. So that is based on their data that they have, and they have done both of the statistical analysis in this. So one statistical analysis is the sensitivity analysis that they have done, that we discussed once, right? And they have done a probabilistic analysis as well in another folder. So they started with that first, our main file, and changed the settings as the sensitivity analysis one. And they have given a water table boundary. So draw max water table and draw minimum water table options are available. So this we can do easily, like they have done. And based on that, uh, basically third water table will come up based on the mean values of these water tables. So what practically is happening is they are giving a slope. Basically, what if you see practically what they are doing is they are simulating a slope where they are they are assuming that this slopes become totally saturated at one stage and totally non-saturated. So water table is lowest here. So basically this slope is not saturated at all, right? And in the maximum case, this whole slope is saturated. So on the basis of that, the simulation actually just took a mean and saw that on in a mean way where the water table can be as half saturated and half unsaturated. So practical relevance of these kind of simulations will be that. Okay, let's continue. So they have defined these maximum and minimum, and after that, basically, they are now defining statistical properties of water table as well. So basically, they will change the normalized mean, and that's how they will do the statistical analysis, right? All right. So let me show you this. So in the statistics, if we go to the water table and the statistical properties are there. So here we can actually give a full distribution of how this mean is calculated. So if you see normalized mean is at 0.5, that means the average of maximum and minimum that will be lying around at the center. It can be actually changed if that is required. It can be at 0.25 or 0.75 as per requirement. And in some cases, uh, if there is a chance, we can actually do if we do a probabilistic analysis, we can actually give a distribution to this as well. So we'll see that also later on. So let's click OK. And what then they have basically computed it simply and found out what it is. So this is where they are basically defining how a normalized mean is calculated here. So the maximum and the minimum water table and the mean water table, basically it's calculated by this ratio that we just mentioned, right? And on the basis of that ratio, they can actually place the mean water table wherever required. So a normalized mean of 0.5 basically produces at center the mean water table. If you give any value between 0 and 1, it will basically shift it towards the minimum or towards the maximum water table value. Okay. We compute it, we save it, we interpret it, and we saw the interpretations, how the sensitivity curve of water table location can be seen. So if you see, let me check it out first. So if you just compute it basically and interpret. So interpretation, it gives like this. So based on the water table, it is giving some factor of safety. And we are more interested into the statistical plot. The statistics, we want to plot how the water table location, if it changes, how the factor of safety changes, right? So in this plot, what it says is from 0 to 1, if the mean water table location changes, the factor of safety reduces from 0 at 0 point, it was around 1.28 or 1.3, and it has gone all the way to 0.6 or less than that in if that full water table is saturated. So what it basically indicates is in case of high saturation or full saturation, the least factor of safety that we can get is around 0.6, 0.6. And in the lowest saturation, where the water is not saturated, the slope is not saturated, for it, what we'll get a factor of safety is 1.28 or somewhere around 1.3. So this kind of a study also is very helpful when we see seasonal water variations. So when water changes level from one season to another, and suppose like a dump slope is there, or internal dump is there, which has this capacity to store some amount of water, or some hydrostatic pressure is developed when suppose rainfall is there, or it has issues in drainage of water and water is stored inside. So these kind of water tables start developing. Now, saying that a mean average of water table is here, that may also indicate that an effective drainage can happen. Maximum it can reach from here, and the mean is here. If we just assume it as a fully saturated, we can assume it as a maximum water table, and this is how all the factor of safety changes. Now, the sensitivity analysis, as we were discussing, that all the other factors will remain constant and only one factor will change. So here also same thing is happening. Only the distribution of water table is changing, how the mean is changing from one place to another, right? And on the basis of that, only the factor of safety change has been given here. Okay. Now, what is next is the probabilistic analysis. So let's see what they have done. Uh, That's okay. Now for the demonstration of probabilistic analysis, they have taken the second material loading and they started the Monte Carlo simulation, and they have used a deterministic water table as mean, and then they have given a statistical distribution. So what they have done is basically they have taken the same thing. Mm, Okay, Amritesh, what I will do is first I will let's see if we can do it here in this, and then we'll see if it is not coming for the second tutorial. Okay, let's see first here and go for the methods. Oh, sorry, the statistics and probabilistic analysis. And in the statistics, when we go to the water surface, we just now have uh, a full statistical that as well. So that can be done, but if we do that now and compute, what we'll see is obviously a probability of failure and everything will be there, but also uh, histogram plots of water table locations with respect to factor of safety can be plotted. So let's plot that scatter plots of right. So okay, we have to select something. Let's check this out. So what this is doing is it is taking let's just start by what they are doing and let's see what happens. Maybe what Amritesh is facing, we are also facing that. Sorry. Let's open the tutorial 2 file, right? And we go to the project settings and we change the statistics to both uh, right and nothing else, global minima, that's okay. Notice that the file as we have read in already includes a deterministic water table. Yes, that we have done. We can incorporate existing water table into that. So go for the statistics and go for the water table, and so we are using the deterministic water table as mean, and we are using the same distribution vector as normalized distribution. I think we have to change the standard deviation somewhere, otherwise it will be just a single thing. As option allows water table distributors. Acha, during computation you face that. Oh, okay. Let me check out. Let's see. Let's try that, and let's see. So minimum ठीक है. The standard deviation they have taken as 0. Uh, what I will do is I'll take it as 0.3. Let's see. No, 0.15 on one side. Okay, and by default use deterministic. ठीक है, draw the maximum water table. The minimum water table on a boundary will then be automatically calculated. So you can draw the maximum if you want. So in that way, do we and it has calculated the minimum. That's okay. So what we have done till now is this example already had a mean water table. Now because we have done a statistical analysis and we have seen we have given a normal distribution to it, basically based on the mean and the maximum value, it has calculated a minimum value. So that is already done. And then what is happening is that's okay, that's we have done. Now observe the maximum water table we have just drawn is defined above the slope surface. Right, we have obtained that. It is calculated. Water table statistics. The statistical distribution of water table is specified by the normalized random distribution 0 to 1. 0 represents this. ठीक है और कुछ I'm just reading through because just want to see why that error came for Amritesh and standard deviation. Yeah, that's what I was see. They all also have put a standard deviation. So because if you don't put a standard deviation, basically it's just a single peak. Single peak means just the mean and all the values are in the mean. So standard deviation has to be put. So I think we have already put that standard deviation as 0.15, right? Yeah. And that's it. So normalized standard deviation is put. So that's what the purpose was. And let's try now if we face the same issue as Amritesh did. Till here, I think we have done. Let's save it as something else, just to make sure other files are not disturbed. Tutorial water table starts. Okay, we do that. We compute. Amritesh, for me, it didn't come. Hmm. You were stuck in this part only, right? When you computed this?
Yes, sir.
Yeah, because I actually could go ahead. Why I could go ahead? Uh, I think my surface option was. Yeah. Do check that because hmm, hmm, try that. Try doing without that. Try doing a circular and that ways. See, only finding non-circular. Maybe that's maybe the reason it was doing. Try doing that and see if you get the same error. So for others, what we have done, we have basically tried doing a probabilistic analysis now. And if you see how the factor of safety is basically very less because of that, and 100% chances of failure. So basically the failure has happened, and let's see what kind of analysis they have tried. Uh, so yeah, something similar. And if we see the histograms, okay. So we can see the histograms, how the probability and the factor of safety of a probability distribution is there, right? We can also see how the probability distribution of water table is there. So water table, how it is being changed. So for our case, we have defined a mean at 0.5 and we basically given our normal distribution between 0 and 1. So that's how the water table is changing. What practically what it means, this kind of distribution basically means that between the maximum and the mean, how much variation is there, right? So if mean is the mean of this is kept here, how distributed the maximum and minimum uh, these water tables will be. So based on that, obviously the factor of safety will change, and that's what it has calculated. So what's the purpose of this? Why we have done here? Why we have done all this here? Basically, probabilistic analysis, again, the concept is the same. When we have very less idea or some idea only of how things will be distributed and we don't know exactly what it will be, we don't know a single value, we know that it can range from this to this. So based on that, basically a probabilistic analysis is done. Probability, how it has defined, basically it has taken a mean and it has, on the basis of the mean, it has basically distributed the values from in form of a normal distribution. We could have changed any type of distribution. We could use triangular or log normal, anything, and it's taken a normal standard deviation. And on the basis of that, it has basically tried to vary the this water table from fully saturated point to a not so fully saturated or a lower mean value of this. Perfect. You got that? Okay. Yeah, I think I think some issues are there. Small things will be there. Do try it again wherever you are facing such issues, and do try to plot those again. Do try to model that again. I think tutorials are good enough to learn what is happening, and also learn why these we are doing, why these kind of exercises given, what is actually practically happening. Practically, it is being changed from saturated to non-saturated district, right? So do check out that. Do check out these tutorials. Anyone has any other tutorial problem? Amritesh, do check out the same thing on the 16th one as well, if maybe that's the problem there also, and see if it works. Okay. If it doesn't, we'll see it later sometime. Okay. Is that okay? So it's working for Swati. Perfect. Awesome. What else? Anyone else had any problems in this tutorials of limit equilibrium? Slide software. Do check those out. Why I'm saying this is because it gives a good idea of what is happening, why it is happening, and why we are doing it. And especially also, it gives us a nice training to do our further simulation works that we'll be doing further on. So uh, do complete if you have not done. What I will do further is not do LEM or slide tutorials later and from now. What we'll be doing later on, because we will be probably starting finite element method, we will be starting something called a phase software. Phase is actually very similar to slide software, but it is based on finite element method. And we'll be learning about finite element method soon, what it is, how it is done, what are the differences in finite element and other methods, what is the concept behind it, and so on. So we'll be doing that, and we'll be seeing how things are different. So that's it for limit equilibrium. If anyone has still any problems, any concerns, any doubts, any comments, any suggestions regarding till now what we have done in limit equilibrium or whatever tutorials you have done, you can discuss now. I'll give you 1 minute before I start the second part of it. I want to actually discuss a case study of how things are done in practical field and how a case of slope stability analysis was done, and based on what kind of situation was there, limitation of data was there, and how we actually interpreted it, and how we could uh, give a suggestion for the solution that was there, how it was implemented. So we'll discuss that in 1 minute. So take 1 minute. If anyone has any doubts, I'm waiting for that. If anyone wants to discuss anything regarding this. After this, we'll start that case study thing if no one has any doubts. Okay, 1 minute. Okay, no doubts. Perfect. Uh, those who have not done, please do this. Requesting you, because it's very useful, very helpful. Acha, who someone contacted me. Ashish, an issue where he has a Mac in place of Windows, so I think that was not working for him. Uh, if he's here, I would have asked what happened, but apparently he's here or not.
Yes,
Kumar,
sir, I'm here.
Kumar Adarsh is there. Where is he?
Yes, sir, I'm here.
So did it work for you?
Sir, not yet, sir. I will try again. I have to install Windows.
Did
Then
you
I
start virtual machine?
sir.
Yeah, do that. Try that
Today I'll do
and
and if
do these exercises.
contact.
Sorry.
Sir, today I will do it, and if I face any problem, I'll contact you.
Sure. Do that, and I think there won't be any. This is simple software, so issues might not be there.
Yes.
We'll see anything else can be done, because I didn't find any Mac version.
Yes, sir. I
So,
also searched, but I couldn't get any.
so for others also, if anyone has Mac or other operating systems, if you're working and you want to use this cracked file, so I would suggest use a virtual machine. Virtual machine is something you can install Windows inside these, and I use that and install the software inside and work. Uh, थोड़ा बहुत मेहनत करना पड़ेगा, but moving on. So do work these tutorials out. We can have some maybe sometime, if anyone has any doubts, we'll look into that on case-to-case basis. Okay. Moving ahead, I will give you now a case study. So if you have heard, there is a bridge and uh, there is a railway line that is being made for connecting the northeastern regions. So I don't know how, if someone is here from northeast in Assam, Arunachal, or Manipur, Mizoram, anywhere. Someone is there from that side? Any representative of our northeastern states? No. So to give you an idea, actually, even till now, there is no direct connectivity of in railways to many parts of northeast region, and even Imphal is actually not directly connected uh, to with the central railway grid of India, even after these many years. So there have been issues. I mean, there are issues of some resistance, local resistance there that do not permit work, and there are many things. Politics is there, and many things are there, and also challenges with regard to the terrain is there, and so on. But I was really surprised when I came to know that. And now government is actually trying to do that. So they are trying to basically build a big set of bridges and tunnels to basically connect that area with the central line. And in one of these sites, they had many of these sites, because uh, it's a mountainous area, right? So many of these sites will have slope stability issues, right? So this site actually, I will show you one uh, image first. Where is it? Yeah. This is an actually a plan or a design for a bridge named Bridge 164 in that northeast zone. Uh, Basically, somewhere near Imphal, not very near, but a little bit ahead. What the situation was, basically it was there were two tunnels. If you see these contour plan, what they have done is there is a tunnel on this left side, oh, the right side, and there is a tunnel on the left side, and a river flows in between. These both are the mountain sides on the left and the right. So to connect those, they are building one of the tallest pier reinforced bridge. So this will be one of the tallest bridges, one of the tallest piers in India that is being constructed there. I think work is quite ahead now as compared to what it was that time. So these are the two mountain ranges. Here are the tunnels, tunnel entry and tunnel exit here. Two tunnels are there, and this was to be connected by a bridge. So presently, when we got this details, the present situation was that these piers were basically being made. So piers are basically sort of basis on which the main bridge will be sustained. Okay. So what the problem was that these slopes you see on the left as well as on the right, both were very unstable, and especially considering we had to construct so many piles inside, right? We have to do extensive construction, and a huge load had to be applied on these areas, right? So a full scale stabilization was required for this kind of slope. Okay. Now, the strange thing was there was the whatever the study was being done in terms of geological and all was summarized in only this chart. So this chart, what they gave us was the only data they could give us at that time, because other reports we said how things and make a station work, how to make a stabilization plan in suppose the left side of the slope. So if you see on the top view here, it if you can, I can zoom in, I think a bit, yeah. So this river goes on the base. These are the two main piers that are there, and there are two piers on the slope and one abutment, similar to pier but very small. Okay, and this is a steep slope and this is a gentler slope on the top, and we have been given some contour plots here. You see, contour maps are given, but all on the non-digital platform, like this hard copy was given to us. Basically, this is a scanned copy sort of. Okay, and in terms of soil, what we were given was something like this. So for wherever they have actually done the construction work, because they have to basically bore the piles first. Above that, they will be, build this piers. Okay, so they have done these piling work inside the ground, good enough depth of more than 15 meter or something. And based on what they found during the excavation, they basically have given us how the soil or the inside profile was there. So they had done it at, because there were three piers along the slope. So 1, 2, and 3 locations we have the data, right? And 4 sets were there for the inside profile or the geotechnical profile of that, and on the top view we had these contour maps. So that's the only thing we had. So that was the huge limitation of data. We couldn't do any lab testing because that time it was tough to bring also samples, and it would have taken time for that time. And they had done some lab testing based on whatever excavations they had, and based on that they had some classifications of what kind of soil it is there, what kind of rock it has we have encountered, and what are their basic geotechnical properties like compressive strength, density, and so on. So we had that data, and we had some location profiles of 5 locations, 1, 2, 3, 4, 4 locations basically on if we consider one slope, about the inside profile, and based on that we have to basically formulate a slope stability map. So how we do that now? The challenge was the missing data, obviously, that because we have just one cross-sectional profile here. Also, we have to like digitize this and extract, right? That is one challenge. What else we could have done is either we could have asked or conducted our own surveys, which would have taken another huge amount of time. Or then what we thought of was, because we have these good profiles of contours are there. So why not we convert these contour maps and convert them into altitude profiles or uh, these profiles which give us in sense the cross sections. So that's what we tried. Starting from that, we basically use these control maps and divided into like 5 or 6 sections. At least 5 sections we divided, right? Taking the middle one as the base, 2 or 3 on the left and 2 or 3 on the right side. So on the basis of that, we had 5 lines, 5 profile lines like this. So profile basically gives us height versus x, height versus the horizontal way. So basically x and y values for the geometry, if you think in terms of simulations, right? Now we had these x and y values for the outer profiles. What to do for the inner ones, right? Inner ones, we had just this data. At 4 locations, we had 4 points that say basically the first type of soil is at 11 meters deep, till 11 meters deep. Second is from 11 to 17. Third is from 12. Third is from this point to this point, right? And fourth is below that. So we had this at 4 locations only. So in order to basically make a graded profile, because if you just simply connect these lines, that won't make sense at all, right? Because the geometry of the slope is also representative of the geometry of the geological profile below. So that doesn't make sense. So what we did was as I said, we made 8 lines total. So in that sense, we basically plotted these lines on the chart and found out their x and y values based on so we had the 0 line in between, and 3 lines on the left, 4 lines on the right, 5 lines on the right, total about 8 lines. And we found all the x and y values for the profile, first step. Second step was about the geological section. So what we did for geology was we basically started some estimation algorithms. So estimation algorithms were very many, but what we followed was the simple grading profile. So what we did was we found the lines x and y values, right, from the contours. So we started that. So suppose this is the second line, the x of the second line is this, the y of the second line is this. So x and y for the outer profile. Now we have the material properties profile at certain locations. We marked oh, we marked those locations and kept them as constant. So we had at 4 locations, so at all 4 locations, we marked these values at constant and subtracted those as per the requirement was there on the main data set that we had. And then we basically started a gradation profile based on the outer surface. So based on the outer surface and based on the difference between these two values, we basically made a smoother profile between these two. So found out the x and y values based on the outside profile and the inside profile. And we'll show you how these things turned out. Mm. So initially we had just this data, and what we got uh, we started like this. So the outer profile was this. Like the second line we could actually make based on something like this, because we use the outer profile data and the data with the differences between at the 4 locations. So even we could have just joined the line, but we actually started making a graded profile according to that. Now, this is for just 2 layers. So we also had for multiple layers. Let me find it out. These are all old works, so I'm basically finding where they are and all. Hold on. Hmm. So this is a cross-sectional profile for line 1. Yeah. So line 1 basically, if I have the profiles, do I have the divisions? Uh, I don't think I have the divisions, but just to understand, we basically divided into 6 parts: 1, 2, 3, 4, and 5 and 6. And this was line 1, 2. This was 0, 3, 4, 5, 6, 7, something like that. So what you were seeing was for line 7, line 1, and you can also see for line 8 we could make like this. So we had all the measurements and all. So some sort of this could be interpreted by uh, the data we received just from that one single figure. We could actually extract all this information based on profiles on the geological data, and we could plot it here. Now, we had these material properties with us, and we could actually do the simulations. So that was easy part. Based on the simulations, what we found was that let me see if I have the fully simulated one or not. Okay, apparently not. I don't know if the material properties are correct in this. But if we actually simulate this, it will take a lot of time because uh, the number of surfaces, the number of the whole extent of this is too much. So this one was actually around 150-meter high, the tall, and the extent was also enough. So we did this kind of study, and what we found were where the slip circles were basically intersecting and what was the height and all. And on the basis of that, we basically tried to find a solution. So that's what I wanted to show you. So the solution that we gave, the initial solution, uh, was something like this. So the the divisions that we were getting were not that deep. So basically the profile was failing along this side. So these were the weak layers. The stronger one was anyways within. So we wanted basically to reach the third layer. So third layer was quite strong. It was compacted silt or soil, something like that. The above 2 layers were quite weak and they had to be basically stabilized. So the solution that was presented here was threefold. Basically, first was these, you can read the SDA. So SDA stands for self-drilling anchors. The self-drilling anchors are something like when you do a drilling operation, you use drill rods and drill bits, right? So self-drilling anchors are actually inbuilt drill rod and drill bit. So you drill the with anchor itself, so it remains there. So it has a sacrificial bit and the whole rod that was acting as a drill rod now acts as an anchor. So the advantage of this is that you don't have to carry double equipment or anything, and you can actually use the same thing and just drill it in. And even the cost also is comparatively less in those, because the amount of strength that is given in SDAs are much better. And the second thing was we wanted to do some chemical grouting work in this as well. So chemical grouting work needs hollow pipes, because from inside these hollow pipes, the chemical grout goes out. So we also proposed a chemical grouting operation that would have covered the nearby areas. So based on that, that was one solution. So this was the pattern that we decided that how what will be the distribution. A staggered distribution of anchors actually helps in basically using less material in covering a larger area. So basically overlaps are ensured in the cross linking. If we do a square shaped distribution, there will be larger gaps. If we do this kind of a staggered distribution, the gaps between the effective area of reinforcement reduces. So generally these days staggered distribution is preferred, again based on what kind of work we are doing and how what kind of we are proposing what kind of solution. And the second solution and the third solution were also given. The second solution was applying, because apart from stabilizing this, we had to basically also take care of the slope on the surface, like the superficial erosion has to be prevented. So there are some surface stabilization measures that are used. So in this case, what was done was we used a geocell type of layer. So geocell actually looks not mentioned here, but geocell basically looks like a crisscross honeycomb structure sort of material. If I can find something for you guys, I can show. Yeah, let me give you that. This is called a geocell. So geocell, what it is a like a polymeric material, some sort of plastic is there that can be actually expanded by opening it. So it generally comes in collapsed forms. If you expand it, it basically spreads in these forms of honeycomb structure, and these can be spread on slopes. Like if you see these kind of stabilization is there, and you can fill this geocells up with material, and what it does is it basically holds the slope positively inside, and creates a sort of a bonding effect between the whole slope surface. So the superficial erosion is prevented, as well as the bearing capacity of the surface also increases a lot, because now you have given some reinforcement here. So the bearing of this area improves, like you can put more load on over it. So even this is much used in railways and roadways also to improve the condition of the sub-base layers and all. So you can fill it with concrete, you can fill it with gravel, anything you want to do, you can do. So basically improves the condition a lot. So this is one way of stabilization. Another, because the greenery was required, a requirement was there, so we also set to put a jute geotextile over it. So jute geotextile basically is a porous material that prevents the soil from falling off. So we propose that we fill the geocells with soil and put a jute geotextile over it. So jute geotextile is like jute bags that are there, na bori, that material. And if you spread that, the surface erosion is prevented for some time. So that was done, and greenery was like plantation was encouraged in that sense. So threefold. So sometimes so many solutions have to be given just for the single slope. So that's what I wanted to show, how a simple slope stabilization work can be done. Now, this was done on slide. Later on, we also did use finite element method to basically see what is the comparative factor of safety between finite element and limit equilibrium. So that also was done later on. So this was a thing. Any questions in this? This something on the practical lines of how we get a case or how we get a problem in field and how we solve it. Where do we get data and all? So this was there in this case study. Okay. Is that okay? You want to want any clarifications, any suggestions, any questions in that? Right? Okay. Now, before moving ahead, what I want to basically do is I was hoping for doing an exercise on limit equilibrium, but I think time is running out. We are already 11:30, 11:20. So won't be doing that right now. But then what I will do is I will give you those questions. You can use them, put them as lab work. These will be simple problems like you did in your limit equilibrium, this slide tutorials. So similar problems will be there that how draw a slope, this dimensions, and maybe we have some questions where geological structure inside is given, properties are given. You have to find the slopest factor of safety and all. So you have to basically do it in slide software. So rather than doing it now, what I will do is I'll give you those questions. You do it and your work, and I'll expect that slide files to be given as assignments. Okay, so that we can check them. So lab assignment can be there. So this also will be coming in your journals, lab journals. Clear? So we'll be supplying that today by evening probably. Like there are 3 or 4 exercises are there, so easy enough, not that tough. Okay, perfect. So let's move ahead. If anyone has any questions, do ask, because we are running short of time. I'm not stopping that much, but do ask if anyone has any questions. So we'll stop and discuss that also. Otherwise, what I want to do is give you a brief introduction of finite element methods. So if it's okay, we'll start that. Anyone has any questions? No? Shall we start that? Okay. Okay, so we have seen different modeling methods, right? So we have seen arithmetic models where factor of safety was calculated using given deterministic formulas, cohesion and friction and weight, and the angle of sliding was given, and you could actually calculate the factor of safety directly. And we also saw the equilibrium models, the limit equilibrium method, when the complexity increased. So as we were seeing on the first side, we were basically making an ideal assumptions of a single planar failure, right? Or maximum to maximum, we were seeing other iterations, like we were seeing the advent of cracks, tensile cracks were there that were doing a failure in conjugation with the planar failure. Or we were doing also some sort of tensile bolting or the tension bolting that was basically stabilizing it. But essentially, in terms of geometry, we were basically idealizing in terms of that it is a smooth profile, smooth slopes are there. There are no undulations, or there is no different shapes or sizes there, or basically the geometry was quite simple, and assumptions were made to keep it that idealized way, right? When we moved ahead with the complexer geometries, we saw how it can be done in limit equilibrium method, right? We in limit equilibrium method, we could actually divide the whole slope in circles, right? And we saw which of these slip circles or the slip surfaces, if not circular, were the main failure surfaces that was giving us the lowest factor of safety. What happens when we have further complexity? If we want to see how things will behave if they're not in a slope behavior, right? We we might have a material that is in a dumbbell shape, or we might want to check how the stresses and strain develop in the shaft of a dumper sort of. So in those cases, we can't just rely on these equilibrium models or the models that are more based on factorosity. We go for a complexer method, and a method that basically encompasses more ideas, and that's what is the numerical models. So numerical models, what they do. So till now we were going for the formula based or arithmetic based approach. We were also using the similar algorithms to find the equilibrium between the forces when we were doing limit equilibrium. But in numerical models, what happens is we basically solve numerical equations or numerical relations. What is numerical relation? Suppose we want to see how heat transfers from one point to another. So from one point to another, what are the factors that are affecting heat transfer? It can be what is the difference in the temperature between 2 points, right? One thing can be there. The second thing is what is the length or the different distance between those two things, and what is the fact and the coefficient of thermal conductivity of this material from which one point to the other, the medium between these 2 points where the heat will be transferred, right? So all these parameters are defined by certain equations, right? So the heat transfer equation will be defining how, at what rate, suppose the heat will be transferred. If K is the coefficient of thermal conductivity, delta T is the temperature, right? So the thermal conductivity equation will define that. Similarly, for our cases, if we want to do a structural analysis, what will be that? It will be something like a stress-strain relation, like uh, stress is equals to E times or the Young's modulus times the strain, right? So those are the stress metrics or the stress equations, or it can be a spring type of equation or a complexer equation that will have a different parameters also. So different conditions like in a structural, in heat transfer, in suppose the fluid motion, which Bernoulli's equation can be used. So in different types of scenarios, there will be some defining equation that will tell in what way things are moving, how the current is moving in a wire, what time it will take, how the fluid is moving, how the heat transfer is happening, how the structural stability is being done, how the movement of the slope is there or the movement of rock is there, or how which equations define that. So based on these equations, we will actually predict all the movement criterias, all the positions, all the accelerations on the basis of these equations. So these are numerical equations or numerical models on which a physical phenomena is taking place. So that is important, and that is the difference between these two. So let's come to that. That what basic differences are there between limit equilibrium and finite element. So in limit equilibrium method, as we were seeing that mostly it is based on the slope stability analysis, because we are more focused on the slope stability work. And it can be used in some other cases as well. We can do for some other analysis, but the whole algorithm is defined for the slope stability work. But finite element, as I said, is based on numerical equations. So any sort of a physical phenomena, be it slope stability, be it a movement of stress and strain, be it movement of air or fluid, so be it heat transfer, be it movement of current, or even wireless communications, anything which are based on any physical phenomena which is based on these governing equations that we can simulate using finite element method. What is it? How is it? We are coming to that. And what happens in that we in terms of geometry, limit equilibrium is just based on simple slope type geometries, because that's the whole purpose of it. In finite element, there is no restriction of what kind of slope, what kind of geometry we have. In the slide software, you might be remembering, we had to actually define the direction of the slope as well. If we do the settings, in the settings, we have to actually define which direction the slope is oriented, because the algorithm is not even developed that much that it can actually predict the direction of the slope. If there is a complex slope that is made that is very unclear to it, it cannot actually do the limit equilibrium analysis. Even if you try doing a analysis where you have two sets of slope, where you have a right side slope as well and a left side slope as well, like we had in this case study, we had two different slopes, right, on the left and the right, but the analysis was done for one side at a time, because in limit equilibrium, the slide software and limit equilibrium analysis, we actually cannot just by the help of algorithms just define okay, these are the slopes, so just find out the slip circles and all, because even that algorithm is not that developed that it can detect where are the slopes. So we have to actually tell them, okay, these are the slopes, this is the direction of the slope, now find the slip circles. That's how that software is designed that way. But for finite element method, we don't do that. We don't find slopes. We don't find any weakness plane or something. It's the fundamental of doing finite element analysis is based on governing equations, right? How the things will move from one point to another, from one point to another. So we'll see that how things are done there. And that's why all kinds of geometry, varying kind of geometries can be actually assessed by finite element. Okay. And divisions, in terms of divisions, it is done in form of slices, as you can see. Uh, the slices are done. So we were seeing how the slide number of slices we had to define, right? And even in interpret after the analysis, we could see what are the slices, and the if we go for the report, we could actually see which are the stresses and the forces that are being developed on each of these slices that were we could see in the limit equilibrium. In finite element, something different is done. Divisions are done, but divisions are done throughout the geometry. So if this is the slope, basically what will happen is it will be first the boundary will be discretized into different segments. So a small, if you can see the red portions, we will see this in more details ahead also. But if you can see here, the red dots are there that are basically representing the discretization points, the divisions that are done. And on the basis of these discretization, a mesh is generated throughout this profile. So meshing and discretization is one of the major what to say indicators of a finite element analysis. So mostly, even though it is done in other methods as well, but it starts from the finite element that we basically divide into, as the name says, finite elements. Number of elements are finite or countable. So we divide the whole geometry into countable elements, and those elements are basically analyzed separately. And then the results are combined, and the results are therefore interpreted. So that's how divisions are done in finite element method. We'll be seeing those in details, how divisions are done, what kind of divisions are there, what are elements, what are nodes, and so on. But just to show the differences between these two methods and how these are different. And as I said, in limit equilibrium method, there is a search for surface of weakness, right? We try to search which are the weak surfaces. Like we try to do a grid search where there is different radii and different centers, right? And we try to find which are the circles that are there and find the factor of safety in each circle and find out which is giving the least or the local minima of that. So we basically try to find the surface of weakness or the whichever surface kind of surface is there. In finite element, this doesn't happen. So finite element method is more based on uh, more based on the physical phenomena, right? So if we say even in the slope stability analysis, if we assume, so what the analysis will be based on stress and strain development. So what is the weight of that, how much weight is cumulative that is coming, and on the basis of that, what are the resisting and driving scenarios of stresses, and on the basis of each of that, each point will have certain stress and strain value, right? On basis of these stress and strain values, actually the failure surfaces are decided. So there is no failure surface that is analyzed in that. All surfaces are analyzed, all things are analyzed, but due to the development of strain, the maximum strain that will be developed in the most critical part of the more critical surface of failure. So the most critical surface of failure will show maximum strain, and that's where we find which will be the point of failure or which will be the surface of failure in that sense. So in a typical slope stability analysis in finite element, we can find that on the basis of stress and strain values only, and not on the basis of factor of safety. But how factor of safety also can be calculated in that case. So in limit equilibrium method, we calculate it directly based on that formula that we have. While in this, there is something called the strength reduction factor. So a strength reduction factor is a way in which we can actually keep on reducing the strength of the material in some ways, and we reach a point where there is a failure, or basically the results don't converge. So as you might recall, we were in rock slope technology, we were studying what are the criterias of slope failure or the slope failure analysis. And one of the criterias was factor of safety, obviously, and then there was a probabilistic analysis. And then there was a critical strain analysis, right? So finite element method, when we talk about the factor of safety in the finite element method, that's where the critical strain part comes up. So at critical strain, what will happen? Basically, the results the equilibrium won't be maintained in a slope. So somewhere or the other, the results won't meet with each other. So suppose there are this slope that we are seeing here. It's basically, if we say, suppose it is divided into 5 zones. Suppose 1, 2, 3, 4, 5, and also like some. So basically, we have these small groups, right? Uh, so each of these points, the stress and strain value will be calculated. If I'm just giving an example that if these kind of meshing is done, so each of these points will have certain stress and strain values calculated. So all the calculations, if the slope is in equilibrium and not failing, all the calculations will basically converge to each other. What does that mean? Convergence mean that uh, the calculations that you achieve from top to bottom, like if you start calculating from this point, that here there is no stress, then there is the stress due to this weight, then there is a stress due to this weight, and so on. Those will be calculated and coming here, then here. All the values will be calculated based on this, right? So the calculations that come from the top to bottom or the left to right, whichever direction the algorithm is there, will also be the same for the other direction. So basically the results will meet each other or converge in case the equilibrium is maintained. In case the equilibrium is not maintained or the slope is not stable, it is basically failing. So in that case, obviously the whole mesh will be distorted or the geometry will also change. There will be certain movement that will not be matched if you calculate from one direction to another, right? So that time it is called a point of non-convergence. Non-convergence means the data is not meeting or the slope is not stable enough. So that threshold after which that doesn't happen is based on what kind of strain is developed. So that kind of analysis we will see when we reduce the strength in the strength reduction factor, we reach that point where the convergence doesn't happen. So the results don't converge and basically the material fails. And the point at which the material fails, that point is considered as the critical factor of safety. And on the basis of how much strength we have reduced, the factor by which the strength is reduced is actually considered the factor of safety of that material. So that's very roughly how we calculate a factor of safety in finite element method. There is no direct factor of safety formula calculation there, but there is this method where we can do a strength reduction, a step-by-step strength reduction, and find out what is the critical strength reduction factor, and that will be considered as factor of safety. So there can be even there can be the factor by which strength will be reduced can be more than one. That means that we are actually reducing strength. Or if it is already failing, we can actually reduce the factor by less than 1 points, right? So if you reduce, if the strength reduction factor is suppose 0.8, 0.8, if you divide something by 0.8, its value will increase, right? So at that time, basically, it suggests that if you want to reach the convergence or the critical point of convergence, you have to increase the factor of safety by certain factor or divide it by a certain strength reduction factor. So opposite of a strength reduction factor becomes a strength increase factor. So in basically strength reduction factor, if in any direction, gives us an idea of what will the factor of safety. Okay. We'll study these in details, how the strength or the factor of safety is calculated, how the strength reduction factor is calculated, how we do basic exercises of stress strain analysis, slope stability, ventilation modeling, and so on. So finite element method is too diverse, and we will be covering few aspects of it. Like we'll be covering the structural aspect where we'll be doing some slope stability analysis. We'll be doing some fluid dynamics aspects in which we'll be seeing how the fluid moves from one part to another, and also how we can do it in terms of simulation of ventilation in underground or somewhere. So that also we'll see later on. So now coming to if you see finite element method, as I said, in terms of how it works on the basis of the representative functions or the objective functions that define that physical phenomena. And those are generally in terms of partial differential equations, right? The PDEs. Don't confuse it with the PDF, that was probability distribution function. So I have to start writing the full terms, I think, if that might confuse someone. So PDEs are generally general terms referring this partial differential equations. So differential equations basically are, as you all know, in the complex phenomena are generally defined in these terms. And if you want to find a solution between certain domains, you have to basically solve these PDEs, partial differentials. And that's how a numerical solution is found. So how do we do that? We first divide the geometry into different segments. So as I was talking, we do something called the discretization and meshing. So comparing it with limit equilibrium, where we were making slices and the surfaces, here what we do is basically divide a model into different elements and nodes. So small elements, the finite elements that it's called. So this is a simulation that we were doing for underground coal pillars. So it's stability of underground coal pillars. So this was a pillar, a complete pillar in which two slices were made for the depillaring work. So we wanted to see that okay, the above overlying uh, overlying material is there, the overburden is there, the properties in terms of the coal is there, and we had excavated some portion in between to simulate the slicing action of that. So how this works and how these things work, basically in why I wanted to show you this is what kind of discretization and meshing we have done. So you see, if you zoom in, you will see various type of meshing is done, and the whole material, every material, all the materials here are divided into elements, like small elements. Here you can see actually triangular elements. So triangular elements are there, and the intersection of these are called nodes. So these two things basically are something where the calculations happen. So if I say, okay, this node is considered as 0, 0, 0, uh, or the origin, and on the basis of that, we actually calculate based on what kind of properties are there of this material, and what is the stiffness matrix is there, or what are the elastic modulus and Poisson's ratio values, and uh, how much stress is there on the whole thing. We can find out the values of the surrounding nodes, right? One is here, one is here, one is here. All the surrounding nodes values can be found, and so on. All the surround nodes can be found in subsequent iterations. These elements are something where uh, the estimations of values are now have to be done. So based on the values that are obtained at suppose node 1, node 2, and node 3, right? The values of this area are estimated based on certain functions. So it can be either an averaging out function, right? So a point here will be having a value of the average of these three. That can be a way, or there can be some basis functions, some functions that actually define how the values will change. So suppose in this linear one, if a basis function is something like from if you say x and y, if this is a linear function, so the value at this point for this node is suppose 1 here, and here is 0. So the effect of this value from this point to this point will be linearly decreasing from 1 to 0. Similarly, there can be a basis function similar to this here. So basically what it means is if A is the value here and B is the value here, so you can actually predict the value based on this linear relation between these two. So something like in between it will be something like 0.5 into A1 into 0.5 into A2. Or here it will be like something like 0.7 into A1 plus 0.3 into A2 and so on. So basis functions basically define how the approximation of values will be done in the elemental part of the finite element. So basically my apologies. Mobile call came and everything got disconnected. Uh, Hold on. You guys can hear me now? Or no?
Yes, sir.
Yes, sir.
Now you can hear? Okay. Okay, we'll try to cut it short now. Anyways, 1150 is there. So yeah, so that's the concept behind how the calculations are done. So based on the governing equations, all the calculations are done in these nodes. And on the basis of basis functions, different basis functions basically calculate how the values between these nodes will be there. So elemental calculations are done on the basis function, and on basis of the governing equations basically are the things that govern the values of each of these points. So if displacement at this node is A, this node is B, so we saw how displacement at every other point can be actually calculated. So this kind of calculations and approximations are done in finite element method. So what we were doing, we were talking about how the discretization and meshing is there. So you do understand now ki because the main calculations are done at these nodes. So as close the nodes will be, the higher the accuracy will be for the results to be right. Higher the accuracy will be there. So if these nodes are very close to each other, every node will have a certain calculation based on the actual equation, right? And the approximations will be less, will be covering less area, and the accuracy of the result will be more. However, again, the thing comes similar to what we saw in limit equilibrium method. More the slices, higher is the computation time. Here, the more the nodes, even higher is the computation time. So more the nodes or more the elements, exponentially the computation time increases. And especially if you have slower computers, it takes much more time. So that's why there is something called the optimization of these meshes. So like if you will see closely, I don't know, yeah, you can see. So if you see closely, the density of mesh which I have kept in this in these pillar portions is different from the density of mesh which I have kept on the overburden and the the below portion, right? And why is that? Is because I am more concerned into what will be the stability of these pillar portions, because I want to see will these be stable, which will they not be stable? Do I have to do more stowing work, or will I have to more additionally support this area in order to excavate or not? So I'm more interested into that. So see how densely I have basically made a mesh here. And as compared to that, the portion here, basically, if you, this is highly like distance between these will be maybe 10, 5 or 10 maybe coming in these two only. So that's how we basically sometimes change the density of mesh. We sometimes change the size of mesh and so on. So in terms of elements also, there are different sorts of elements. We can do different kind of meshing. We can divide it into triangular portions in 2-dimension geometries. We can do it into four, like a square or rhombus or a rectangular portion. In 1-dimensional geometry, like a heat transfer type of problem, we can have just a single line or that. Acha, in a single element also, we can have multiple nodes in between as well. So this basically what it does is it also calculates the main values in these nodes. So if in a triangle, if we put more nodes here, so this is called a 6-node triangle element. This 6-node triangle element will be calculating the position, calculating at 6 positions from the governing equation. So basically, only the approximation is done in this zone, and this value is already known. So basically, more accuracy. But again, calculation time increases in this way also. However, the number of element is less, single element and more nodes. So approximations will be same as compared to if we had more triangles. So like if we have divided it into like a triangular element, the total number of elements also increased. So 1, 2, 3, and 4 elements were there in a 6-noded single triangle. So that's how we can actually uh, increase the accuracy as well as decrease the computational time in that sense. So again, based on what kind of application we are doing, if we actually need that kind of accuracy or not. Okay. The three-dimensional sort of elements are there if we do a three-dimensional geometry analysis. So similar case here also, in three-dimensional also you calculate at these 3 points, and basically you get that the values approximated in between. So the concept is same even in 3 dimension. Also in 2D as well as 3D, we can have second order elements. So second order elements, what does it mean? Basically, even the mesh shape can be altered, even the single elements based on what kind of nodes we have positioned. So this is helpful when we have similar kind of geometries there, like if we have a circular geometry, right? And if we divide it into simple triangles, that maybe not be that representative of the properties that are on the outside or the boundary conditions. If we have that curvilinear elements, that also sometimes are helpful in suiting that kind of geometry. Okay. So based on that, what kind of work we are doing, we can have these kind of geometries also. So I'll stop here. We have a lot to discuss, but let's not throw that much information here right now. It has been a long class today already. So let's stop here. Till now, we have just started finite element. So it's a we see how it is a little bit different from the previous examples that we were seeing, and how the calculations are done. Unlike single equation, these are governing equations for physical phenomena that are calculated at different nodes, and based on nodes, they are basically assumed at other positions based on different functions. So we'll be learning more about what are these functions, what is basis function, what are the boundary conditions, where they are applicable. We'll be seeing some examples. We'll be using a software called Slide. So after a few demonstrations of the Slide, sorry, we'll be using a software called Phase 2. So Phase 2 is a two-dimensional finite element analysis software, which generally we are using for geotechnical purpose only, like slope stabilization, tunnel work, and so on. Then we will also be using ANSYS, that is a three-dimensional setup. We'll be using that. If time permits, we'll also see the RS3. That is a advanced version of Phase 2, and that also helps in three-dimensional work. So a lot of interesting things we will be doing now, and things will be a little bit not tough, but more technical. So easy to understand, but yeah, technicality will increase. So gear up for that. We'll be covering this part here in computational because it is much more than slope stability. Many things we will be doing apart from slope stability. So trying to cover this part here. In slope stability, we'll be doing now the geological part. So we'll be meeting at 3:30 now. So see you all there. I'll stop here. If you have any questions, any problems, any doubts, please feel free to ask. Otherwise, let's close the class. It's already 12 now. Time is up. Okay. Thank you so much for being here for so long. Thank you for your patience. Do take care of yourself. If you have any problem, any doubts, any things, we can have enough time to discuss. Do feel free to contact. Okay. And yep, that's it. Do take care that lab journals have to be maintained. And do inform anyone who is not attending regularly to at least try to attend some live sessions, because in that way we know everyone is at least able to attend that. Okay. Thank you guys. Thank you so much. Thank you everyone. See you all at 3:15. Okay.